This is an example problem for conservation of momentum for Auburn Physics 1000, summer 2013. So here's the example problem we solved in class. We have an initial situation where a train car, which I've just drawn a box for, train car here, is moving with some momentum P1. I should say it's moving with some velocity V1, which yields a momentum P1. And we have a train car sitting here at rest, which has also some momentum. It happens to be 0 because it's at rest. But first we'll write down that it has some momentum P2. And then afterwards they're going to collide and stick together. So you have the system here where it has some momentum P3, which is the total mass M3 times some new velocity V3. And what we're being asked to find is V3 here. So we know everything that happens before and afterwards we want to find V3. So let me erase some of this stuff. So on our given, I haven't put any numbers here. That's okay, we don't need numbers. What I've said is that we know M1, we know M2 because those were given. And M3 was not given, but we know that if they stick together and they move as one, then the total mass, M3, is just going to be the sum of the individual masses, M1 and M2. So we know M3. We have to do a small calculation to get it, but we know what it is, no biggie. And V1 is given, and V2, like I said, was given as 0, and I've just drawn that it equals 0 to remind ourselves that it is 0. Of course, if we had numbers for all of these, this is where I would put them, is in this section here. But we don't. But I do know that V2 is 0, so I'm just putting it there to remind myself that it is. And my unknowns, of course, V3, that's what I'm being asked to find. So, in this drawing, which I've had to make a little cattywampus because the limitations of the screen, this is my system before. Let me get a different color. This is my system afterwards. Make sense? The blue is before the collision, the red is after the collision. In fact, I'll just write that explicitly. A for after, in the blue, B for before. Okay, so how do we solve this problem? And the answer is conservation of momentum. Anytime you have some sort of collision problem like this involving momenta, that should be the first tool that you pull out to see if you can use it. 9 times out of 10, you will be able to use it. Conservation of momentum is a very, very important concept. So, what is the conservation of momentum? Simply that the total momentum beforehand, so let me go to a new screen, and I will write this down. Total momentum beforehand, which in our situation is P1 plus P2. P1 is the momentum of the car that's moving. P2 is the momentum of the car that's not moving. So this is the total momentum before. In fact, I'll go ahead and do this. This is the momentum before equals the total momentum afterwards, which is P3. So in the colors that I've used on the previous page, this is after. So this is nothing more than the conservation of momentum law. I haven't done anything new or groundbreaking here. I've just applied the conservation of momentum. The momentum before equals the momentum afterwards. So now I'm in a position to apply the definition of momentum, which is just, as you recall, P equals to mv. I'm going to apply that to each of these terms. And in effect, I'm going to unpack P1, P2, and P3. So P1, if I remember what it is just M1V1, P2 is M2V2, and P3 is M3V3. It's handy to make your subscripts match up like that. So I'm just going to unpack these. P1, sorry, wrong. So unpacking P1 gives me M1, V1, and then unpacking P2, I have plus M2, V2, and then I'm going to unpack P3, M3, V3. So the first thing we do as always is we apply, first thing after we write down our equation here, is we apply our zeros. And in this case we only have one. It's the velocity of the second car here. That is equal to 0. So if the velocity is 0, the momentum has to be 0. So I'm going to just cross this guy out because he is going to 0. The little arrow with a 0 is something that we do to remind ourselves that that's 0 without having to rewrite the whole equation, which I'm going to do anyway. So that leaves me with M1 V1 is equal to M3 V3. And I think you probably see Now I can solve this for V3. V3 equals, and I'm going to write it like I did in class, M1 over M3 times V1. And I've written it like this for a very specific purpose, like we mentioned in class, just to remind you of our discussion. Let me get another color here. Here we go. This term right here, M1 over M3, is going to be some sort of fraction that's less than 1. How do I know that? Well, as we pointed out in class, M3 is a combination of M1 and M2. So clearly, M3 has to be bigger than M1. And in any sort of fraction, if your denominator on the bottom is bigger than your numerator, you have a fraction whose value is less than 1. As an example, 1/3. The denominator here bigger than the numerator here, so this fraction is less than 1. So if you look at this thing from a mathematical standpoint, what we're saying is that the final velocity here is going to be some sort of fraction of the initial velocity, and the fraction is determined based upon the masses. I should point out at this point our problem is over. You plug in the numbers and you get your answer, but I want you guys to see the physics that's going on here. So M1 over M3 is some sort of fraction that's going to be applied to the velocity, and what this actually says is that the final velocity is going to be less than the initial velocity, and that makes perfect sense. I think if you saw a situation where a train car hit another train car, the second one being at rest, and they sped up, that wouldn't make much physical sense to anybody. I mean, there's no sort of engine pushing it. If we're going to assume that it's on a level plane and not some sort of hill, it makes no sense for the system to speed up. And if you think about it, if you think back to Newton's laws, you can probably figure out why. So the reason is that once you add mass, in other words, you have this mass here that's moving, and then finally you have a much bigger mass here, M1 plus M2. Newton's first law says that if you increase your mass, you increase your inertia, and it's harder to get the thing moving. In other words, it would take a bigger force to make it accelerate. We're not specifically talking about forces here, but the physics behind the reason that the system slows down is that it's got much more mass and it's got much more resistance to motion. It does not want to move because of the great mass. So that's why you find that the final velocity here is a fraction of the initial velocity here. And no surprise if you know Newton's first law, that fraction is based upon the ratio of the masses, the beginning mass and the ending mass. Because in this, you can look at this thing as that the mass changes. It starts out small as M1, and then it ends up big as M3 because you added that other train car. Okay, see you next time.